Good morning. Laurent's series, the continued part of the complex analysis. Let's go for it. Lesson 1. Laurent's theorem. First, we need to discuss about the series, its definition, its regular part and the principal part. So, we are defining the series as let Z0 be a complex number, a series of the kind summation n going from minus infinity to infinity on an z minus Z0 the power n. This is called the Laurent series at Z0. And by a Laurent series around infinity, we mean a series of the type infinite summation n going from minus infinity to infinity an 1 over z the power n. So this is a Laurent series around infinity, right? If Lz is a Laurent series around Z0 in say infinity, which means in a complex extended complex plane, then principal part of the series is the sub-series corresponding to n greater than equal to 0. For the positive values of n including 0, we are having the principal part of the series. And regular part of the series, the sub-series corresponding to n strictly less than 0. That will be the regular part. Fourth is, the series Lz is said to be convergent absolutely uniformly if its regular and principal part converges absolutely uniformly. Right? Fifth, the regular part converges and represents a holomorphic function in a disk z minus z0 less than r. Suppose you are having a point z0, a disk centered at the point z0, having the radius r, so inside this we are having the regular part. And the principal part converges and represents a holomorphic function in a disk z minus z0 greater than r. Strictly that means outside this disk. Now we are going to start the Laurent's theorem. What the theorem says is, suppose Fz is analytic in the annulus z minus z0. This is your annulus between r1 and r2, right? Then the representation Fz is equal to summation n going from minus infinity to infinity on an z minus z0 the power n is valid throughout the annulus. Furthermore, the coefficients are given by an is equal to 1 over 2 pi iota integral over c f of t over t minus z0 the power n plus 1 dt, where c is any simple closed contour contained in the annulus that makes a complete contour clockwise revolution about the point z0. Let me explain this with a diagram. Now here is the proof. Suppose I am having the point z0 and I am having this annulus, that is this part between circles C1 and C2. This is your annulus, and we are having two circles C1, C2, and inside I am having the point z0. The first circle is, or you can say your first disk is having the radius r1, and the second disk is having the radius r2, and I'm having a point z between this annulus. This is your annulus, right? And this circles, these are in counterclockwise direction, and I'm having this c as a closed contour in this annulus, right? So let's start with the proof. Let z be any point in the annulus r1 less than z minus z0 less than r2. I have to choose r1 dash and r2 dash such that r1 is less than r1 dash, which is less than equal to this z minus z naught, the disk, which is less than equal to r2 dash less than r2. So what we are having? I'm having this radius r1, right? And I take r1 dash just slightly greater than this r1. Let's suppose my r1 dash would be up to here, just slightly greater than this r1, and r2 is greater than r2 dash. That means my r2 dash lies over here, slightly less than this, very close to this r2. I take here r2 dash. It's very close to r2. So now if fz is analytic in the annulus having the radius r1 and r2, then can we say that now fz is analytic in the closed annulus, this r1 dash less than equal to z minus z naught less than equal to r2 dash, right? So now I am having a closed disk, right, whose boundary consists of two circles, C1. What is C1 circle? It is z minus z naught having the radius r1 dash, and C2 circle, z minus z naught having the radius r2 dash, right? So this is a description of the annulus. Now the next step is, by Koch's integral formula, we know that f of z is equal to 1 over 2 pi iota integral over c2 minus c1, because we are having two circles, f of t over t minus z dt. T is any point on the circle C1 or either on the circle C2, right? So which is further equal to 1 over 2 pi iota integral over C2. I break this integral, f of t over t minus z dt. Now in this first integral, t is a point on C2, minus 1 over 2 pi iota integral over C1 f of t over t minus z dt. Now in the second integral, t is the point on the circle C1, right, on the boundary C1. For the first integral, t is the point on C2, and for the second integral, t denotes the point on C1, right? Clear? Okay. Now consider the first integral in 1. Take this as your 1. I consider first integral in 1. For t on C2 and z in the annulus, we have, let's have a look. For C2 circle, I am having the point t here and a point this z in this annulus, right? The red color point. So we have for that 1 over t minus z. Take this equal to 1 over. Just add and subtract z naught. You get t minus z naught minus z minus z naught. I have added and subtracted z naught, which is equal to 1 over t minus z naught. Take this common from the denominator. Wait. Let me write this again. Sorry. This is equal to, I am taking t minus z naught outside from the denominator common, and this will be 1 minus z naught over t minus z naught. Right? Then next, which is further equal to 1 over t minus z naught, and taking this denominator in the numerator as an expansion, 1 minus z minus z naught over t minus z naught inverse. Now this is your expansion. See, 1 minus x inverse is equal to 1 plus x square plus x cube, so on. And I can sum up this as summation x to the power n, where n starts from 0 to infinity. So I'm using this in this result here, 1 over t minus z naught, and this is nothing but your sum, and going from 0 to infinity, z minus z naught over t minus z naught the power n. Okay, so furthermore, see, this is also t minus z naught. Let's take this inside and we will get, there is no n, so we will get this summation to be z minus z naught over t minus z naught. This will be, power will increase by n plus 1, and here it is n. Right? Okay. Next step is, I have to multiply both the sides by ft over 2 pi iota. So I multiply 1 over 2 pi iota ft over, I'm having in the left hand side t minus z. Check. I'm having at the left hand side 1 over t minus z. So I multiply both the sides by f of t over 2 pi iota. So f of t comes in the numerator and 2 pi iota in the denominator. F of t over 2 pi iota into t minus z. Now on the right hand side also multiply 1 over 2 pi iota summation n going from 0 to infinity, and taking ft inside as it is not dependent upon n. So this is first write z minus z naught the power n, and then f of t over t minus z naught the power n plus 1. Doesn't matter. Alright. Now since the convergence is uniform on C2, so therefore term by term integration is valid, and hence we integrate now both the sides. Integral over C2 f of t over t minus z dt is equal to 1 over 2 pi iota summation n going from 0 to infinity z minus z naught the power n, and now integration C2 f of t over t minus z naught the power n plus 1 dt. Fine. This is equal to summation n going from 0 to infinity. I take this 1 over 2 pi iota ft over t minus z naught the power n plus 1. I take this whole as my coefficient an, which is the coefficient of z minus z naught the power n. Now accept this, put whole this as your an, the coefficient, take this as your coefficient an and mark this as your 2, where I must write your an is equal to 1 over 2 pi iota integral over C2 f of t over t minus z naught the power n plus 1 dt. This is your an, and where n is going from, this is very important, 0, 1, 2, so on. Similarly, we have to consider the second integral in 1. What is 1? Here, first we have done, now consider the second integral. The similar steps are there. Now t is on C1 and z in the annulus, right? We are having the point t on C1 and z point in the annulus, and we have Now here I am having the minus sign, 1 over t minus z, which can be written as 1 over, yes, z minus t, right, which is equal to, again I have to add and subtract z naught. So I add and subtract z naught, z minus z naught minus t minus z naught. Fine. Now again taking z minus z naught common from the denominator and taking the rest denominator to the numerator as a expansion. So this is equal to 1 over z minus z naught 1 over 1 minus t minus z naught over z minus z naught. Taking this to the numerator, this is equal to 1 over z minus z naught 1 minus t minus z naught over z minus z naught, right, which is further, again this is your expansion, so this is further equal to 1 over z minus z naught. Now taking this expansion with variable m going from 0 to infinity. For the first integral we take n. For this integral I am taking, for this part I am taking m. So this is t minus z naught over z minus z naught the power m. Now again collecting the terms in the denominator, we will be having 1 over z, okay, z minus z naught will, this is summation m going from 0 to infinity t minus z naught the power m over, the powers are added now, z minus z naught the power m plus 1, right. Now multiplying both the sides again by ft over 2 pi iota, right, same steps I am considering, we get minus 1 over 2 pi iota ft over t minus z, because I am having the minus sign in the LHS in the left hand side when I start my step C. I am having minus sign over here. So now I am multiplying both the sides by f of t over 2 pi iota. So this is minus f of t over 2 pi iota t minus z, which is equal to this. I multiply here also ft over 2 pi iota. Now since the convergence is again uniform on C1, so term by term integration is valid, and hence we get minus 1 over 2 pi iota integral C1 ft over t minus z dt is equal to, I integrate both the sides now, 1 over 2 pi iota summation m going from 0 to infinity integral C1 on ft t minus z naught the power m into 1 over z minus z naught the power m plus 1 dt. Now taking this dt inside and collecting this integral, and 1 over z minus z naught the power m plus 1 rest remain there only. Now put this m plus 1 is equal to n now. We get 1 over 2 pi iota summation m going from 0 to infinity, this integral C1 ft t minus z naught the power n minus 1, because I put n equal to m plus 1 over here. So m will changes to n minus 1. 1 over z minus z naught the power, instead of m plus 1 I should write n. Fine. And here m, instead of m equal to 0 I must write n equal to 1. Why? Sorry. For m equal to 0, here if m is 0 then n is equal to 1. So my summation starts from n going from 1 to infinity. Is this clear? Okay. Next. Which is further equal to 1 over 2 pi iota summation n going from 1 to infinity. I collect this integral and z minus z naught the power minus n. The denominator will be in the numerator now with power minus n. So this is equal to summation n going from 1 to infinity. Now collect this whole as your a with the base minus n with z minus z naught the power minus n. This is my second coefficient. Mark this as your 3. Right, where a minus n is 1 over 2 pi iota integral c1 ft over t minus z naught the power minus n plus 1 dt. Sorry, this is minus n plus 1. This is, yes, minus n plus 1. Alright, next, now substituting 2 and 3 into 1. Our main equation 1, I substitute the values, I will get f of z is equal to infinite sum an z minus z naught the power n plus the sum starts from 1 to infinity a minus n z minus z naught the power minus n. Right, which is equal to f of z is equal to collectively n going from minus infinity to infinity an z minus z naught the power n. Mark this as your 4. Where an is equal to 1 over 2 pi iota integral c2 ft over t minus z naught the power n plus 1 dt for values n going from 0, 1 to 3. And a minus n will be equal to the second coefficient bn 1 over 2 pi iota integral over c1 ft over t minus z naught the power n plus 1 dt, and n is going from minus 1, minus 2, minus 3 so on. This is your not n plus 1 but minus n plus 1. Here you are having minus n. So in the power also minus n plus 1. Clear? Okay. Now choose any simple closed contour C contained in the annulus that makes a complete revolution about the point Z0. So we have chosen a dotted closed contour C in the diagram. See, this dotted closed contour, I have chosen this C. Right? So since ft over t minus z0 is analytic in the bounded annulus by the closed contours c1 and c2 by c, right? Your ft over t minus z0 is analytic in the bounded annulus by the closed contours c1 and c2. Here also you are having a dotted closed contour c. So now you can say that ft over t minus z0 is analytic in the bounded annulus by the closed contours c1 and c, and also c and c2, right? So by Koch's integral formula, let's get back to our page. See, since ft over t minus z0 is analytic in the bounded annulus by the closed contours c1 and c, c2 and c, right? So by Koch's integral formula, the coefficients an may be computed by replacing c1 and c2 by c, right? Thus, an is equal to, we can write 1 over 2 pi iota integral over, not on c2 but it is replaced by c. C1 can be replaced by C, C2 can also be replaced by C. We can compute this an by replacing this by C. So this is f of t over t minus z0 the power n plus 1 dt. Now I can write for this n is starting from 0 plus minus 1 plus minus 2 so on, because now the contour is C, right? So the values of n is positive, negative and 0 also. Again, since r1 dash and r2 dash be chosen arbitrarily close to r1 and r2. Yes? These are chosen very nearer to r1 and r2 respectively. So f of z is equal to n going from summation n going from minus infinity to infinity an z minus z0 the power n, where an is this with n equal to this. This is valid for all z in the annulus, z minus z0 between R1 and R2, because we have proved this in the closed disk. What is my closed disk? Z minus Z0 less than equal to R2 dash and greater than equal to R1 dash. I proved the theorem with this closed disk, and because these are very nearer to R1 and R2, so the coefficient an is valid for all the z in the annulus R1. That means Z minus Z0 in R1 and R2. Right? Here ends up our result. In the next video, I will be doing some examples based on this Laurent series. Well, actually, your application is important for the Laurent's theorem. Only application is important. So go through the proof again with all the steps. It's very easy. Just go step by step and you will get how to prove the result. Thank you for watching this video. Have a nice day.